Okay, let's unpack this. Think about the world, everyday rules. Now, imagine zooming way, way in, and those rules just, well, dissolve. That's the sort of mind-bending place we're exploring today based on that introduction to quantum mechanics course. We're talking about the physics of the really, really small.
Quantum mechanics, yeah. And it's essential because, the physics we use for like baseballs or planets, classical physics, it just completely fails when you get down to atoms.
It breaks down.
Totally. It's a fundamentally different set of rules for that tiny scale.
Got it. So our mission here is to pull out the core ideas, the really head-scratching stuff from this quantum world, and figure out why it matters without needing a PhD afterwards.
Exactly. Make it make sense as much as quantum mechanics can make sense.
Right. Let's maybe start with this wave-particle duality thing. What's that about?
Okay, yeah. So the basic idea is that tiny things, electrons, photons, little bits of light, they can act like both waves.
Like ripples on water, spreading out.
Yeah, spreading, interfering with each other. But they also act like particles.
Like tiny billiard balls hitting one spot.
Precisely. Localized impacts. And they can be both, depending on how you look, which is weird.
Okay, the classic example is the double slit experiment, right? That one always gets me.
Oh, definitely. So you fire single particles, one by one, at a screen with two narrow slits in it.
And you'd expect just two lines on the detector screen behind it where they went through.
That's the classical expectation, yeah. But what you actually get is this complex pattern of many lines. An interference pattern.
Like waves would make.
Exactly like waves interfering. It's as if each single particle somehow goes through both slits at the same time and interferes with itself.
How's that even possible? One thing, two places.
It really messes with our intuition. And that leads nicely into superposition.
Okay, superposition. That's the idea that a particle isn't in one definite state until we measure it. It's like a mix of possibilities.
You got it. It exists in a kind of probability blur, simultaneously being in multiple states or locations until an observation forces it to choose one.
Like Schrödinger's cat, alive and dead at the same time. That thought experiment.
Exactly. It's a famous, if maybe slightly morbid, illustration of how strange this is. Observation fundamentally changes the reality, or at least collapses the possibility.
Oh, okay. Still processing that one. But then there's entanglement, which sounds even stranger.
Yeah, it arguably is. Entanglement is when you have two or more particles linked in this really deep way. Their properties become connected, intertwined.
Linked how?
So if you measure a property of one particle, say its spin, you instantly know the corresponding property of the other one, no matter how far apart they are.
Instantly. Faster than light.
The information about the correlation is instant, yeah. It's not communication in the classical sense, but it's a connection that seems to ignore distance. Einstein famously called it spooky action at a distance.
But it's real. People have shown this works.
Oh, absolutely. It's been confirmed countless times in experiments. And it's not just weirdness for weirdness' sake. It's key for things like quantum computing and quantum cryptography, making unbreakable codes.
Okay, so it's not just theory. This all sounds incredibly abstract, though. Is there, like, a ton of math behind it?
Well, yes. Quantum mechanics is inherently mathematical. There's something called the wave function.
Okay.
Which basically contains all the information about a quantum system. It tells you the probabilities of finding the particle in different states if you were to measure it.
Probabilities, not certainties.
Exactly. And that ties into the Heisenberg uncertainty principle.
Ah, I've heard of that one. That's the thing where you can't know certain pairs of things precisely at the same time, like where a particle is and where it's going.
That's the one. Position and momentum. The more precisely you measure one, the less precisely you inherently know the other. There's a fundamental limit built into nature.
A limit to our knowledge.
Or perhaps a limit to how definite those properties are simultaneously. But even with this uncertainty, these quantum rules are what make a lot of modern tech work.
Really? Like what kind of stuff?
Well, think about semiconductors. The transistors in your phone, your computer, they rely on quantum effects. Lasers, too.
Lasers, like in barcode scanners?
Barcode scanners, DVD players, fiber optics, even complex medical surgery. And MRI machines in hospitals. Quantum mechanics, atomic clocks, GPS, all quantum.
Wow. So it's actually everywhere under the hood.
Pretty much. And the really cutting-edge stuff is quantum computing, which promises to solve problems that are just impossible for current computers.
So it's not just philosophical weirdness. It has real power. It definitely forces you to rethink reality, though.
Yeah.
Certainty goes out the window, replaced by probability.
It does. It shows a reality that's interconnected in strange ways and fundamentally probabilistic at its core. But despite how counterintuitive it feels,
Yeah.
it's one of the most accurately tested and successful theories in the history of science. The predictions it makes are incredibly precise.
But there are still things we don't understand. Big questions left.
Oh, absolutely. Huge questions. Like, why is quantum behavior random? Is there a deeper layer? And the biggest one is probably how to connect quantum mechanics with Einstein's theory of gravity, general relativity, a theory of everything.
Still searching for that one.
Still searching. That's where a lot of fundamental physics research is focused today.
Okay, so wrapping this up. The quantum world. Totally different rules. Things are waves and particles. They exist in multiple states at once until looked at, and they can be spookily linked across distances.
Duality, superposition, entanglement.
And there's a fundamental uncertainty, but these bizarre rules are behind so much of our technology and pushing future tech like quantum computers.
That's a pretty good summary. It's strange but powerful.
Definitely strange. Okay, here's something to leave you thinking about. Given that the micro world runs on probabilities, how might that make you question the solid cause and effect you usually assume operates in your everyday macroscopic world?
Interesting thought. Does that apparent certainty just emerge from underlying probabilities? Something to ponder.